Hello, thanks for inviting me to talk. I will be telling you a little bit about Renyi Entropy of Coulombic systems, work that I did with Jeremy McMinnis and Brian Schwingle. But first, I thought it would be a shame if I didn't say a little bit about some release node calculations I've done previously, given all the sign problems that other people have been talking about this week. This is going to be for systems with fixed ions, and we're going to do release node on the electrons. I'm not going to go too much into all the details of the method. I just kind of want to show you some of the results and some of the issues we deal with in trying to do molecules and electron gases. So this is sort of a standard release node calculation for molecules, or what a molecular calculation would look like, and it's not so different than some of the other traces that people have shown this week. In general, when we do release node, we start with a fixed node diffusion Monte Carlo population. We institute a guiding wave function. We let the walkers react to the boson ground state, and we try to project out the antisymmetric component before the error bars blow up. So if you see on the left here, this would be our fixed node energy. You see that we're decaying in energy, and hopefully we get a plateau before the error bars blow up. There are two time scales on this graph: how fast it decays to the ground state and how fast the error bars grow. The decay to the ground state is mediated by the fermion ground state to the first fermion excited state of the same symmetry. And as everyone knows, the error bars grow according to the difference between the fermion boson energy gap. And I'll show you a little. What system is this? This was lithium hydride. This is one of the easier calculations that I worked on. And this was a really bad wave function. I just wanted to see, how well I could do. And that was sort of the theme of all the work that I'm going to show you in a minute. So there are some easier release node problems. Not, sign problem always kills you in the end. But back in 1980, the date's wrong here. I guess this was 81 or 82. Separately and Alder did the interacting electron gas. They did it with 50 to 60 electrons, and they were able actually to get quite a converged result. So on the graph here is the trace of the energy of two different wave functions that they looked at, and they just want to show that they would converge to the same energies, and they do more or less. But other problems that we might be interested in are a little bit harder. What's that? Okay. Other problems we might be interested in are a bit harder. So molecules, and there's been a lot of chemistry shown in the last week, so I'm also interested in some of these systems. So you can see some of the most notable calculations done from 84 to 1996. Hydrogen is actually a decently easy problem, and you can get quite converged results, but when you start going up in Z, so lithium-2 and hydrogen fluoride, you can see the calculations look pretty decent, but the error bars are quite large. They certainly look like they've decayed in energy, but within the error bars, they may not have decayed in energy. Also, this is Arne Luchow's data. It's not clear that he has a plateau yet or what's going on in the data. So it's really difficult or was back then really difficult to do these calculations. And Bernie and Jonathan and Randy were like, let's try and put more modern computers on these problems and see how well we can do with release node. So we decided to do the first row dimers, lithium-2 to fluorine-2, include 6 to 18 electrons. We didn't do Green's function Monte Carlo. We did regular diffusion Monte Carlo, so we had to do time step projections. But you have to be very delicate with these things. But we did all the projections as well as we could. There are exact estimates available for all these and a lot more, actually, given David Feller and a lot of other people have done a lot of thermal chemistry work. So we sort of knew if we were getting close or not to the right results. And there's some details of the calculations here. But all of this is published maybe 1 or 2 years ago, if you want more details. So one of the nice results that maybe is somewhat illuminating as to why these problems get so hard is we actually did calculate the fermion boson energy gap. So this is what ultimately controls how fast your error bars grow as a function of imaginary time. Typically, this is just a rule of thumb. You want to at least go in imaginary time, at least 1 AU at the very least, if not longer. So with lithium-2, where a fermion boson energy gap was around 3, with fluorine-2, it was around 200. So there's literally, the error bars are going to be not hundreds of orders of magnitude, but around there in difference if I were to try and get fluorine-2 compared, the error bars for fluorine-2 to be roughly the same size as lithium-2 at 1 AU in imaginary time. So we're looking at a huge scale of computational complexity. And we did some modeling of why the fermion-boson energy gap looks like this, and it really is quite physical. The fermions, when you impose antisymmetry, they form shells. When you allow the fermions to become bosons, they literally just fall to the bottom of the well. They don't get this kinetic energy penalty, and you really get this huge difference in the fermion-boson energy gap. So just to show you some of the data, with lithium-2, this was our first shot at things. We actually have better results, but we just took Cyrus-Summergard's wave functions from 1996, not even the best ones he had, and we wanted to see how well we could do and how far we could go in imaginary time we just didn't want to spend more computer time, essentially. And even though the error bars look pretty good here, and that, yeah, maybe we could go further, the population is exploding, so the calculation gets quite expensive as you go in imaginary time. And at least with our first shot, I mean, it's kind of plateauing out, but you couldn't really say this is a fully converged release node calculation. For fluorine-2, it's quite a bit worse. I guess I should point out the time scale here is 1 to 3, so we're able to go somewhat far in imaginary time, at least as far as we thought we should be going. With fluorine-2, you'll see the what is an exact estimate? Yes, yeah. So if you look at David Feller's papers, he has all the thermal chemistry stuff. So they do some experiment, and they subtract out the finite temperatures, they subtract out spin-orbit coupling effects, they do all this stuff, and again, estimate of what the quantum chemistry result would be if you're just to do the Hamiltonians that we're looking at. Extracted from experiments. Yes, yes. But very delicately, with a lot of care to try and match up correctly. What are the best quantum chemistry methods for this? For fluorine-2? It's much better than this, but this was, Cyrus's stuff from 1996. Cyrus's stuff is much better than this right now, and then Miguel's stuff is even better than that. So I think that 5.2. You don't even get to the fixed node here? Oh, this is my fixed node. Oh, that's your yeah. So I think the results. Yeah. The results in the last few years have gone around 9952, I think. And I think that's either from QMC or some form of coupled cluster. Maybe DMRG. I don't know if people have done DMRG CT on it yet. But anyways, our point wasn't to necessarily just set the all-time record for these things. It was to see how well we could do and what were the bottlenecks. But, why didn't you go further on this? Because I don't see the error bars growing yet. Yeah. Well, the population was humongous. So if I changed my trial energy and made I changed how fast my population was growing, I could go further. Well, we had to make some determination for. So you're not keeping the population constant. You're letting it grow along this. Yeah. This is very expensive. But I mean. What most people do, and I didn't really think about it too deeply at the time, but maybe it would have been better, is to not let the population grow so quickly and go further in imaginary time. But when I did my initial tests, I tried to optimize where there's a lot of details here, but I tried to figure out what to do. Yeah. Okay. I'm not going to be able to go that much further in imaginary time, even if I didn't. But also, each generation is getting more expensive for it. Yeah. So just to give a quick summary, I know I'm not going to go through all the numbers here or anything, but this is the imaginary time. As I said, there's some trade-offs, and I tried to optimize my computer time to what I think I could actually calculate. And then, in the background in my head, I said, well, I want to do maximum entropy. I want to do other calculate correlators. So I need to get small error bars on a lot of different quantities. So going further in imaginary time can be done, but I didn't do it. But you can see how much I did. So starting at 3 and ending at 0.035 for fluorine-2. This was, given the experimental values, how much we thought how much we actually decayed, how much we should decay if the experiment is dead on. And these are the percentages that we were able to go through. So we got 60% at lithium-2, 17% of the remaining correlation energy at fluorine-2.
Sorry, that percentage is the
From
gain by releasing node?
It's the difference between what we thought we would gain, given the experimental, the exact result, and what we actually gained.
Yeah, but yeah, doing release node.
Yeah, doing the release node.
Your reference is the fixed node. Yeah, that's what I mean.
You
take the fixed node, you take your release node.
Yeah.
You refer this to the difference with the experiment.
Yeah.
Well, how much of that he gained?
Yeah.
Right. There's this difference. That's 100%, and how much of that he gained by doing the release node? Right. The fixed node and exact is the 100%.
Yeah. So it would be the percentage I was able to go from here down to experiment. Yeah. Okay, so we actually did a lot more than this. We didn't just stop here. We tried a lot of things. We did a lot of max-amp stuff. We tried to do some cancellation, which I guess Mal will talk about more next week. We tried doing non-local pseudopotentials to get rid of, we thought maybe that would alleviate this fermion-boson energy gap. Not a lot of it worked particularly well, but I'd be happy to talk about it during the discussion session if people have.
It would alleviate the boson fermion gap.
But the Hamiltonian then becomes, or the propagator has its own sign problem, and it's quite bad actually, to the extent that I haven't even published that work. So
you didn't do the T move?
Oh, you do T moves, but instead of adding the positive part back onto the diagonal, you just, or the negative part onto the diagonal, you just make those negative moves. And it's quite interesting how bad that can be, at least for harder pseudopotentials. Local pseudopotentials, you're pretty good. Like you can just go and run the stuff, say for silicon or something that you have a half decent local pseudopotential for. All right, so this is all. I just want to give a brief overview of what release node stuff that I did, and other people can ask me questions either now or during the discussion. But what I really wanted to talk about was entanglement. And I'm not sure how many people really know about this stuff, so I'm going to give an overview. Hopefully you guys will learn some new stuff here. So this has largely been coming through from the theoretical physics community. And I sort of got into it when I realized that you could do some quantum Monte Carlo with this stuff. But over the last 10 years, there's been a lot of methods developed. There's a paper by Chris Henley in 2003 that's all Grassmann algebra, and I slogged through it to figure out how to do all this stuff. And then 2004, there's a paper by Ingo Peschel that literally summarized Henley's paper in maybe 2 or 3 equations, and that's the one that gets all the citations now. So this is all for single determinant non-interacting systems. There's some theory as to what should happen with entanglement. Now I'll go into more details in a minute what I mean by entanglement. What should happen to it for Fermi surfaces, and there's something called the Witten conjecture that people have looked at. And some other methods came out to calculate entanglement using fluctuations of particles. And I guess Haldane really popularized the entanglement spectrum back in 2009. So I'll tell you a little bit about a lot of these things. These things aren't really that new, entanglement. I mean, there's methods. DMRG is based off of calculating entanglement and entanglement spectrums. And there's also a new paper by Garnet Chan that density matrix embedding theory that also makes use of these entanglement ideas. But for us, the key thing was in 2010, Malko showed for a spin lattice how to calculate quantum entanglement, and we were able to figure out how to bring that stuff to the continuum. So let me give you a brief overview of what entanglement really is, then I'll show you some of the equations. I'll show you how to do it in quantum Monte Carlo, and I'll show you some of the results that we've had. Okay, so because I'm going to show you some molecules, I'm going to give you a molecular example. And the basic idea of spatial entanglement goes like this. So let's say we have 2 systems that are really far apart, like 2 hydrogen atoms. And we know they're not really interacting. We know the Coulomb is long range, but they're neutral systems, so they're not really interacting with each other. A pretty good wave function to write down would just be sort of a product or an anti-symmetrized product of wave function in region A and a wave function in region B. Fine. But as we start bringing these systems closer together, we know a lot of physics happens. We get to the bond-breaking region, we get to a van der Waals region, we get to a region where bonds start forming, I should say, and we eventually get to the covalently bond region if it's a covalently bonded system. And we know that we just can't write the product of some states in region A times the product of some states in region B. And even if we allow for, say, really complicated states in region A times a complicated state in region B, it's not going to be a very good wave function. This doesn't allow fluctuations or correlations between the particles and the two subsystems. And what entanglement really is about is the number of states you need to accurately write a wave function down when you partition things in space, in region A and region B. And the question is, how many of these things are important? And entanglement is going to be literally functional of these values here. So if we have one of these, if we have Sn equal to 1 and all the others are 0, then that's a non-entangled state. That's two disjoint states, systems in space. And it's only when we start needing to do a lot of these to write down the wave function, or a good wave function, do we start getting entanglement in our wave functions. And these S's, we're going to find these states come from a spatially reduced density matrix, and these S's are also related to that. So I'll show you that on this slide. All right, so this is the formal, more formal definition of entanglement. What we're going to do, and I show a lattice model here, but it can be real space, we're going to partition our space, our Hilbert space, into two regions, A and B, and we're going to have spatial partitioning here. So A is the screen region, B is this other region. And what we're going to do is trace out everything in region B and have a density matrix that's left over in region A. You may think, well, that's very simple, but it's not. I mean, if you've been in the mindset of doing particle density matrices, you might not quite understand how to do the spatial density matrix. Integrating out a full particle, we all know how to do. What happens when you try and integrate something out in space is you get multiple particle sectors that all contribute to your density matrix. So just to give you an example of what these particle sectors look like, this looks like a standard 1RDM integral. But the difference here is that the coordinates I'm integrating over here are all in region B. And the coordinates that I'm keeping only exist in region A. So in this way, I can calculate all the one particle matrix elements that just belong in region A. And I've integrated out all the information in region B. But because I'm going to have multiple particles in my system, I'm going to have a two particle sector. And it's the same thing again. These coordinates for the two particles all exist in region A. And what I'm integrating over exists in region B. I have to do this for all possible particle sectors to get my full spatial reduced density matrix. And that's pretty much how it goes. Not that we're going to actually do these integrals explicitly, but you could, and you would get your density matrix. So here's the important things to take in mind. So I've told you what the density matrix we're interested in. Now I'm going to define some terms about that density matrix. So the entanglement spectrum are the eigenvalues of this density matrix. The entanglement entropy is this function of the density matrix, which you can think of as a sum of row or eigenvalue log eigenvalue of all the eigenvalues in the density matrix. And the Renyi entropy is this function. And the only reason I'm telling you about Renyi entropies, or I care about Renyi entropies, is because I want to do interacting systems. I want to do it with quantum Monte Carlo. And I can't access this quantity with quantum Monte Carlo. I can only access the Renyi entropies with QMC. But that's OK, because a lot of the information stored here is very similar to the information stored here. And for purposes of this talk, we're just going to use this as a substitute for the entanglement entropy, and we can discuss that approximation or issues with that as we go a little bit further. But one of the reasons we can do this is because all the Renyi entropies are served as lower bounds for each other. So S1 is greater than S2, so on and so forth. And we've also done a lot of testing to see how different these things are. Also, there's when we go to do extended systems, they show the same scaling laws. And I'll tell you a little bit more about what that means, too, as we get there. OK, so practical methods for calculating entanglement, there were three that I really looked at. And the last one here is the QMC one. I'll tell you about it in a minute. There are two others. I also use QMC to calculate this one, the fluctuation method. But both of these are only exact for single determinant wave functions. But you can get the entanglement entropy. This one is exact for any wave function, but I only can get the Renyi entropies out of it. So just to give you a quick feel of what the correlation method looks like before I go to the quantum Monte Carlo. The reason I'm showing you this not just to show you all the methods, but I think it gives you some intuition as to what we're doing, or what the entanglement looks like in a wave function form.
Before that, can I ask a question?
Mm-hmm.
We think of entanglement as a measure of correlation, right? But a single determinant wave function has no correlation. So you're including sort of exchange in the correlation now, in your definition of correlation?
This is a great question. Let me just, I think I can answer this, but tell me if I don't. There are all sorts of different density matrices that you can look at. And we know that, I mean, if you just look at the full density matrix for any Hamiltonian, just all n particles, that would have an entanglement of 0. There's only one state, the ground state, and you just have one term in your density matrix. You could look at the 1 RDM, the 2 RDM, the 3 RDM. You could look at spatial. You could look at a spin density matrix. All these are going to have different entanglement properties. And what I'm looking at here is specifically the spatial density matrix. And when you look at the spatial density matrix, you can have very large entanglement, even for Hartree-Fock wave function. So something like DMRG, which is based off looking at wave functions that have low entanglement, doesn't work in higher dimensions, partially because very simple wave functions can have very large entanglement. Not necessarily complicated entanglement, but large entanglement. So did that answer your question?
Probably.
OK. OK. Maybe this example will a little bit too. So let's try it. So I'm going to give you an example of a particle in a well. OK? We know what the solution is, and I've solved it on a grid. OK, so I know it's a little off center, but I have my infinite boundaries. It's in a box. And what I'm going to do is say I want to calculate the entanglement by slicing the system down the middle. I can do any partitioning I want, but I'm just going to do it down the middle for now. And what this correlation method and what Ingo Paschal and Chris Henley were able to show is that for a non-interacting system, all you need is the 1 RDM to calculate the entanglement. And the way it works is you calculate your full 1 RDM, and you partition it such that you only keep matrix elements that exist in region A. You diagonalize that, you get the eigenvalues, and you get the eigenvectors.
Which one's region A?
So I'm calling this region A, but I could have called either side. So we'll do the left side is A, right side is B. And this is where it ends. Forget about this extra part there. OK? But I can do the same for region B. I could this upper right quadrant. And I can get also the eigenvalues and eigenvectors for that region. And you can show pretty easily that the eigenvalues will be exactly the same. And it doesn't matter what partitioning. So I did split it in half. I do have mirror symmetry. But when you do this entanglement stuff, it doesn't matter which region you actually go and calculate the eigenvalues for. They're the same on both sides. So what happens is, I've shown you the prescription for calculating these quantities. You can actually rewrite your wave function, your Hartree-Fock wave function, in this basis. And let me just really emphasize here. These things, they're orbitals that only exist in region A. Not like an exponential tail that goes into region B. They only exist in region A, and these only exist in region B. And you can actually rewrite your Hartree-Fock wave function in terms of these orbitals and the eigenvalues that come out. So this is the form. And you'll see it's a product of these different modes. These are all, these pair up with each other. So I get a product of this goes here, and these two go here. And I get a product of all these 5 different things. So I'll have 2 to the n number of terms. So it's exponential. But that's OK, for now at least. So for the example I showed on the left, I split my wave function in half. And there is literally a 50% chance I'll be in region A, and a 50% chance I'll be in region B.
No, when you say that the orbitals leave only region, this means that essentially the boundary that delimits your region is some sort of hard wall again, in this case?
I mean, it's not a potential thing, but it is a hard wall. I mean, in terms of where the orbitals actually exist. So you wouldn't necessarily want to try and construct your wave function in this form for something off lattice, because you have to worry about continuity and things like that. Right. But as a post-processing, we can actually do this. Okay. Yeah. In DMRG, they actually do construct the wave function in this form. And they're actually doing it in the continuum nowadays, so there might be, it might be not as bad as I think it is. But right now, I'm not suggesting you create your wave functions like this. I just want post-process. Okay. So that was the one electron example. And the two, let's say we put 2 electrons in the well, and I didn't write down the wave function, but you guys know how to do that. And I cut down the middle again, and they're not interacting. It's Hartree-Fock and everything. Again, I'm going to get something where in this form. And what you can see here is that you can literally read off the particle fluctuations from this wave function. There is a 1/4 chance both particles are on the left-hand side. There is a 50% chance I get one particle on the left-hand side and one particle on the right-hand side. And there's also a 1/4 chance I'll get all my particles on the right-hand side. So what you see with the Hartree-Fock wave function, and it's what you pointed out a minute ago, there is no correlations, essentially. And you can explicitly see that by looking at, say, let's just look at these 2 terms here. Oh, whoops. Yes. Just let's look at these 2 terms here. Both of them have a particle on the left-hand side, A1. What's the probability that the second particle is on the right-hand side? It's the same. So particles can just, if there's Coulomb interactions, there would be repulsion. If you had a particle on the left-hand side, it'd be more likely your second particle would be on the right-hand side. With Hartree-Fock, you don't have those sorts of correlations. So the entanglement can be large here, mostly due to fluctuations on the Hartree-Fock level. And only when you do a multi-determinant wave function or when you include interactions do you get, you're no longer in this form, this product form, and you can get correlations among your expansions in this form of the wave function. Okay?
So if you calculate the entropy of this, it would be?
This system?
Yeah.
This is log 2, and this is 2 log 2. I'm pretty sure, yes. This is definitely log 2. I'm pretty sure this is twice. Yes.
So the entropy that you're defining is basis dependent?
Well, I wouldn't say that. It's dependent on my partitioning, but that's it. I have some solution of my wave function. Let's say I have the exact wave function.
No, but if you partition orbital space or K space or something,
then the entropy is 0.
I don't want to partition orbital or K space right now. That's okay. It depends on what density matrix you're looking at. Right. So it could be the one RDM would have a different entanglement than 2 RDM, then the spatial, then a spin, then a combination. You can integrate whatever degrees of freedom out that you want.
But that's generically true of any definition of entanglement in more than two dimensions. Okay. It depends on what.
Well, it would be in 1 dimension too.
I mean, it seems like it would be nice. Okay, I'm not an expert on entanglement. It would be nice if it were just like a kind of like a physical property of the system. So it should be functional with a wave function.
I mean, you're saying it's meaningless to say that this system is strongly entangled because it depends on what you choose.
Oh, I would say it's not meaningless to say it's strongly entangled in space.
Because space is meaningful. And that's, I mean, in general, when we talk about, I just teleported this particle from Switzerland to UK or something, they're talking about a spatial decomposition.
Yeah.
They're talking about, and that's what they mean by entanglement.
But the usual definition of entropy would be 0 for a pure wave function, right?
If I took my boundary to be the right edge here and had all my wave function.
In usual statistical mechanics has 0 entropy.
Sure, yeah. Yeah. So the equivalent here would.
The universe is in the pure wave function. It has 0 entropy.
So what I'm doing holds for pure wave functions. If I slice my system in half.
Not the wave function of the universe.
No, but what you just said, I mean, I agree.
No, but if I look at
the universe in a
the
wave function, right?
He's integrating out 1/2 of it, so he doesn't have a pure wave function.
yeah, you look at the use
stuff.
I started with a pure wave function. I mean, but once you start integrating out degrees of freedom, no matter what density matrix you're looking at, the 1RDM, 2RDM, whatever, you're always going to have entanglement. You're always going to have a bunch of eigenvalues not just equal to 1 and 0. You'll have some a series of eigenvalues once you start losing some information. Okay? Okay. Let's see. Oh. Okay. I'll give you some motivation about why I'm interested in this as we go a little bit further. It's not just an exercise. Well, maybe it is, but I don't consider it just an exercise in calculating something. I think it's actually useful to look at spatial entanglement. Okay. So how do we calculate this in quantum Monte Carlo? So as I mentioned, there was a paper in 2010 with Hastings and Malko and a bunch of people at Santa Barbara and elsewhere, where they showed how to calculate the entanglement, spatial entanglement. So that's the other thing here. We already know how to calculate 1RDMs and 2RDMs. Calculating spatial entanglement hasn't really been done, and it's been sort of an open problem, at least in the physics community. And it was in this paper that they really started showing how to calculate it in space. So they did it for a spin system, but it can be easily, as we showed, extended to continuum systems. And it's based on doing a replica trick. So you're going to increase the dimensions of your Hilbert space from 3n to 6n, and we're going to have 2 copies of our wave functions. And we're going to define something called the swap operator that swaps spatial configuration. So I'll tell you what that means in a sec. This is formally what this integral looks like, and I'll tell you what the alpha and betas are in the next slide. No need to get bogged down right here. And you can rewrite this thing so you can sample it in variational Monte Carlo with 2 versions of psi squared. And then the operator for the entanglement would look like this. And the main thing just to take out of this is that I'm just evaluating a trial wave function at 4 different points in space. But I'll tell you what those 4 different points in space are on the next slide. Okay. So what we're going to do is variational Monte Carlo. We're going to optimize our wave functions, get the best thing we can, and then calculate the swap operator. And we're going to do it by having 2 copies of the wave function that we're propagating in VMC. So what I'm calling alpha 1 here are the coordinates of the electrons. So let me say this again. I am doing a division in half. I'm doing the half space. This is a dimer molecule, so these are, I guess, 2 beryllium atoms, if you will. And I have 4 electrons for each beryllium atom, 8 electrons total. So what we're going to do is have 4 electrons, and alpha 1 is going to represent the electrons on the left-hand side. Beta 1 is going to represent the electrons on the right-hand side. And same for the second wave function there. And what we're going to do is start copying over the coordinates, beta 1 and beta 2. And we're going to swap the coordinates from alpha 1 and alpha 2. Okay, so my numerator or my denominator here are the initial wave functions that is sampling with VMC. And the 2 functions in the numerator are where I swap the coordinates of the electrons in region A and B, or I mean in region A with each other. So what does this look like, or why is this meaningful? So let's say I do this swap, and I go to evaluate this quantity. And this quantity doesn't change very much from this quantity. And this one doesn't change that much from that, which is to say I swap my coordinates. But the electrons on the left-hand side didn't care that it's seeing a new set of electrons on the right-hand side. The wave function is roughly the same. Well, you'd say you'd say that the wave functions are roughly unentangled between the left-hand and right-hand side. But if I swap the coordinates and the wave function changes a lot, or the product of the wave function changes a lot in the numerator, then it really did matter what the configuration on the left-hand and the right-hand sides were. And that would give you a heavily entangled state. So the way this generally works is if you start evaluating configurations and you get a lot of configurations that are close to 1, you're going to have a very unentangled system. But if you get values that are close to 0, then you have a very entangled system. And this also comes up in terms of the fluctuations. It's not just the wave function. If you swap your configurations and you have more electrons and less electrons in one configuration now than the other, then that's, we're not in Fock space. This is canonical wave function, so that would give you a 0. So fluctuations cause entanglement to be quite large here. So that's sort of the intuition behind what the swap operator does. In VMC, all the walkers are independent, so it's really not necessary to have two populations. You can just have your regular VMC population and do the swap every X number of steps. Just make sure you don't swap your walker with itself.
So if you do a bad swap, can you get a 0 in the denominator then?
Well, I mean, in VMC, this is the denominator here is what you're sampling. Okay. So you generally don't sample 0, or you never sample 0. Absolutely not. So that won't happen. But you can get 0 in the numerator. And you can get actually negative numbers in the numerator. But because this ultimately is equal to the density matrix, all the eigenvalues of the density matrix are between 0 and 1. So as you average over the entire system, you will get a number between 0 and 1 for this estimator. Right. So I guess I have 15 minutes. This should be fine. So I'm going to tell you about the entanglement of molecules. And my intuition, and the reason I was interested in this is because I always felt that, well, I mean, a lot of people, a lot of the discussion on bonding is about how electrons in different molecules correlate and fluctuate with each other. So the study of bonding is essentially about how electrons interact between two or more regions of space. And entanglement really, the spatial entanglement is literally how wave functions are partitioned between different regions of space. So I was somewhat interested in if entanglement was a good way to describe bonding in molecular systems. And I'll tell you what that means more in a second. But I guess the first thing to say is, what is the definition of bonding? And if you go to the IUPAC website, you'll find out there really is no definition of bonding. So this may be an exercise in futility, but I was still somewhat interested in going further. But if you did go to the website and you read what they had there, you'd find that they say bonding and bond order are related to this quantity here, which is the 1 RDM and the overlap matrix for, I mean, these all come from the quantum chemistry community. These are things you calculate in a typical Hartree-Fock calculation. But they won't say this is what bond order is. And largely, they use this definition because in this paper, Mayer in 1986, he came up with a definition of bond order that is largely based on these sorts of quantities. So I should just remind the audience, bond order in particular refers to something very specific. It's, in chemistry, they say it's literally the number of electrons involved in a bond. You may remember that carbon-2, depending on who is teaching you, has 2 or 3 bonds. Nitrogen-2 has 3 bonds, yes. Hydrogen-2 has 1. So there's certain, yes, I actually have it right here. So there's certain well-established, or I guess agreed upon numbers for certain systems. But it's really not that agreed upon for all sorts of quantum systems. And so, Igor Mayer had his paper here. But people keep trying to define new bond orders and new ways of describing bonds. So guys may be familiar with chromium-2. It was synthesized, I guess, in the mid-2000s. And it's really one of these, maybe the hardest molecular problem in all of quantum chemistry, at least that we know of right now. So Roos decided to go and redefine a new bond order for transition metal type systems. People started recently trying to define bond order for ionic systems. No one has really tried to do it for van der Waals systems yet, or very strongly interacting systems, but there's sort of this idea that we should have some measure of how many electrons are involved in a bond. So in some sense, it's an evolving idea, and I'm going to try and tell you that entanglement is actually maybe the better idea of, to describe bonding, not just for covalently bonded systems, for all of these, and to discuss extended systems also.
For van der Waals, wouldn't you say 0?
No.
Isn't it bonded? I mean, is it?
Well, very weakly. It's not a normal,
But you'd say it's maybe small, but non-zero, right? Okay. These are the sort of discussions that are maybe, if we can put math down, that'd be one thing, but they may be more philosophical in nature, and that's sort of why I don't like doing this sort of research, but I was sort of just interested in trying to see what I'd get out of this.
I've got a question related to that. So if you do know the bond order, what exactly do you do with that?
So at least for where it's defined, like well-defined for a lot of these systems in covalently bonded systems, they use it to sort of associate energies for breaking bonds. So you have all sorts of carbon systems that can form, and there are this many bonds in this complex, or this many bonds in that complex. That gives you some idea about how strong that bond is. And
to make a fast first-order estimate of.
Yeah.
So carbon, for example, can have different orders of bonds, and the carbon-carbon distance changes according to the bond order. The higher the bond order, the shorter the bond.
Yeah.
So you can classify that, in this compound, it's this order bond.
If you're on a long plane ride, get Linus Pauling's book and read it. It's like a novel.
Good advice, yes. But on the other hand, if you...
It's not a long novel, though.
It is long.
On the other hand, if you just want to take up the theoretical idea that I can define number of electrons in a bond, and you don't care about usefulness, that's where I stand. Yeah.
Well, and you'll probably say it, but I mean, it's useful to the entanglement entropy is useful if you want to think about the optimal breakup. Say, I need to break this system up into parts. What's the way I can do that to minimize the?
But I guess my question is more towards, if you were to calculate the bond order to 3 digits, would anybody care?
Accuracy isn't necessarily an issue here.
Well, the original definition bond orders were integers.
Yes. And
Already exact.
but on the other hand, we're not talking about digits here. I mean, we're talking, there's literally maybe 5 or 6 widely used bond order methods. I mean, these aren't widely used yet as far as I'm concerned, but there are other ones. This one is very widely used. Beta analysis is widely used. There are a couple others that are widely used. Just single Slater determinant, counting bonding and anti-bonding orbitals is widely used. They're maybe not so much anymore, but it used to be. So if you run these different methods, say for nitrogen 2 even, beta analysis will tell you there are 5 bonds in the N2 molecule. This will tell you there are 3. I mean, but that's a simple example, and that we all know the beta analysis is just giving flaky numbers there. But for things like beryllium 2, I think beryllium 2. Yeah, it's beryllium 2. The chemistry is quite complicated, and it's very multi-determinant and very highly interacting. And we need something that's maybe consistent for strongly correlated or very weakly correlated systems. So some of these orders give 0, some of them give 1, some of them just don't really give anything that makes sense on beryllium 2. So that's sort of where I'm coming from now.
No matter what the definition is, always an integer?
No. A lot of times it is, and I'll show you some. So if you count bonding and anti-bonding orbitals, that's going to give you an integer, but that's sometimes a good approximation. I'll show you in my results why that's a good approximation. So integers do come out a lot. Okay, so this is sort of how I wanted to connect to the idea of bonding. And this is in the mean field, I know, but I only have a certain amount of time. And this was just the easiest thing for me to get you guys making the connection between entanglement and bonding. So there's a paper in 2011. This stuff was known well before 2011, but this particular form was published in 2011. You can calculate the entanglement entropy if you know these mu n's. So this is a known quantity, this is a known quantity. You want to take k to infinity, so these are just some coefficients. But these mu's are dependent on your wave function. And they are given by these, they're cumulant expansions of the fluctuations. And they're given by these equations here. So this is literally the number operator for the number of electrons in region A. So if you were to evaluate this configuration in this form, you'd get 4. But these things can fluctuate. So you can get 3, you can get 2, you can get whatever. So you integrate you VMC sample your wave function over all the fluctuations. You can get the first mu1. And then you do the square and the cube and so on and so forth. And you can get all the higher order moments of the fluctuations. You can actually use that to calculate the entanglement entropy of a non-interacting system. Exactly.
Sorry, I don't understand what you've written. NA there is
The number of electrons in region A.
Can I put it out of the integral?
Not if your electrons fluctuate between region A and region B. So you can imagine I have another picture here where there are 3 electrons here and 5 here. So it does matter what configurations you're looking at. Right. OK. And what was shown in actually 2006 is that the fluctuation method for an interacting system is a lower bound for the actual entanglement entropy of the system. And I'll show you why that's important to me on the next slide. But here's the thing. So the ab initio bond order paper that I showed, the Mayer paper, it was shown maybe a year after the paper came out that his method for non-interacting systems also, and only non-interacting systems, reduced to particle fluctuations between regions A and B. So these aren't the same formula. But if you're willing to go to the entanglement, you get something that's based on the eigenvalues of the spatial density matrix as opposed just to the fluctuations. And you get numbers that are very similar in a lot of the cases that I tested. So at the very least, maybe I can make this more formal, but there is some connection between that. And it's largely because for non-interacting systems, there's not much more than fluctuations between both sides that you're going to get in bonding. I mean, there's no correlations. So this is kind of a neat definition for what bonding is in the non-interacting case. OK, so here's what I'm going to define as a bond order. So remember, we're literally trying to figure out how many SNs are important in order to write a wave function partition between 2 sides of the system. I don't just want to count the non-zero values here because a lot of them might be close to 0 and unimportant. So the entanglement, literally L log L, or I mean eigenvalue log eigenvalue, is a measure of how many of these are actually important to the system. So I'm going to define the bond order as the entanglement over 2 log 2. So the reason there's this value in the denominator, the 2 comes from standard chemistry. There are 2 electrons in a bond. The log 2 comes from that particle in a well solution I showed you before. If you slice, if you slice, should I just keep going? Or? OK. If you slice a single particle wave function in half, the maximum entanglement you can have is log 2. And you'd have that, say, for H2+. You'd have that for any single particle system in which you just slice your system in half. That would be the maximum entanglement you have. All right, so there are a lot of reasons I like this, but I have to speed up a little bit. So I'll just say there's, well, I can tell you more about this later. For the many-body system, this all comes from a many-body density matrix. There's rigorous definition of 0 bonding. We can use any spatial partitioning. So yes, I'm showing you half spaces, but say you have some complicated system, and you want to know how one part of it's connected to the next, maybe a hydrogen that's bonded to some lattice. You could slice through that, something like that. For the systems that I tested against other methods in which, say, nitrogen 2, carbon 2, well, carbon 2 not, nitrogen 2, hydrogen 2, things that are well defined, I get things that are very close to what other, or exactly what other methods get. So what I'm going to show you is, for interacting systems, is S2. And I find where I can test this for Hartree-Fock, they're not so different. So for now, I'm just going to use S2 as my substitute, because that's what I can calculate. OK. So for molecular systems, I did all the singlet ground states for the first row of dimers, lithium 2 to fluorine 2. We tried with a lot of different wave functions just to see how sensitive we are. So we did Hartree-Fock. We did CAS-SCF. We optimized the JASTRO with CAS-SCF. And then we optimized JASTRO and all the CAS-SCF coefficients. So we actually have a very good wave function for carbon 2, or for all of these, I mean. Ignore the correlation part here. That's from another talk. It's a whole different beast. Because correlation method really can't be applied to interacting wave functions. I showed you what it was before, but the results here aren't that useful for what we're about to discuss. But keep in mind the fluctuation method, which is rigorously a lower bound for the actual entanglement. OK, so on the left-hand side, I have what the Renyi entropy is. On the right-hand side, I have my definition for bonding. For lithium-2, nitrogen-2, fluorine-2, where a lot of the methods agree, except beta analysis doesn't agree here, but whatever. It's pretty well established that this is 1, and this is 3. And if you look at the right-hand side, I'm literally spot on with that. If we go and look at more controversial molecules, I get beryllium-2 as this. Beryllium-2 is really this highly interacting weakly coupled system, and I get a fractional bond for that. For carbon-2, I get something that's a little bit more than 3. And that's actually not that controversial, but I'll tell you why it is a little bit. And if you compare it to, say, that's the Renyi entropy. This is my bond order on the right-hand side. If you compare just to quantum chemistry with a really bad basis set and Hartree-Fock, you'll find that they also get a lot of these results. And if you do multi-determinants, things like that, a lot of these things agree. But you'll see for the ones that are strongly correlated, like beryllium-2, they just get weird numbers for this. And a lot of the methods actually give 0 for beryllium-2. So there's some interest as to investigating this more, but also carbon more. And also when you do Hartree-Fock, they get 3.3. And this is all the ab initio bond order results. This is the Mayer paper again. So let's look at carbon-2 a little bit more right now. And as you can see, with my multi-determinant everything, I get about 3.2. They get 3.3 with a single Hartree-Fock. What's going on there? And carbon-2 is actually kind of an interesting system to a lot of chemists still. So this came out last year. And they claim there are 4 bonds in a carbon-2 system. And they're doing some what's it called? Well, it's a multi-determinant wave function. It's a CAS level calculation. And we wanted to look at this a little bit more ourselves. But all within quantum Monte Carlo right now, I can't get the full spectrum out. If I could get the full spectrum out, I could tell you more about it. For the Hartree-Fock carbon-2, I can get the full spectrum out. And I know Hartree-Fock really isn't what we want to look at, but let's just start there. Let me tell you a little bit about the entanglement spectrum for carbon-2. So on the plot here, I have the eigenvalues, and it's not really the eigenvalues. I'll tell you what it is in a second, but it's related to the eigenvalues of the reduced density matrix, the spatial one. And this is the distance, so I'm stretching the C2 bond. At equilibrium here, I got to stop in a minute. At equilibrium here, that's what this black line is. What you see is the following. So first things first. There are literally 2 to the 12th number of eigenvalues for 12 electrons in their spatial reduced density matrix. What I've plotted here is a reduction because not all of them are independent. And the number of independent degrees of freedom is just 12. So I'm showing the important information here. There are only 5 lines that you can see, right? All of these are doubly degenerate due to spin. The middle one is quadruply degenerate. So there's 12 eigenvalues total here. The one at 0 is a perfectly covalently shared mode. So these would correspond to electrons that are 50% on one side, 50% on the other side. Things that are close to 0 but aren't quite at 0 are either polarized on the left or right-hand side a little bit. And the red lines here that are far away from 0, don't contribute to the entanglement at all, at least not even here, not on this graph. Eventually, if you keep shrinking the distance, they will. And they are the core electrons. They're the 1s states. So the thing that's different about carbon-2 than a lot of other systems is that these green lines don't exist for most other systems. And I shouldn't say most other things that we've tried. Let's say that. And these 2 green values do contribute significantly to the entanglement at the equilibrium distance. So if you were just to count the number of modes that are contributing to the bonding here, there's 4 at the blue line and 2 for each of the green lines. There are 8 modes. It would be, if you do want to use that as your measure for bonding, then at least at the Hartree-Fock level, you would say carbon-2 has 4 bonds. It's quadruply bonded. And what we did is we ran this for the other 3 systems or 4 systems that they said would also be quadruply bonded, and we see the same structure. And for things that they said they weren't quadruply bonded, we get we don't see these green lines come in. So it looks like there's a signature of what they're calling quadruple bonds even at the Hartree-Fock level.
So don't see green lines mean that
they're
either 0 or they're very far.
Yeah, and these partially, maybe like 25-75 split, they're just a little unusual. They don't come up a lot. Okay. What we'd really want to know is what's happening in the interacting system, though. So what I can tell you is this. This is, again, ignore the correlation lines. This is carbon-2 being stretched again. This red line here is the Hartree-Fock. So it corresponds to the entanglement that I showed you for the previous, or for this. What happens when I turn on interactions, what happens when I put all the multi-determinants, my best Jastro, optimized everything is, first off, the fluctuations go down. And